Hello everyone, this is Greg Risterman from Olympus OSSA. I'll be your host today for this webinar entitled Beyond the Elements, XRD Mineralogy and XRF Analysis for Advanced Mud Logging. Our presenters today are Jose Broom, a field sales engineer from Olympus, and Don Snyder. Jose is a field sales engineer and has had nearly 30 years of experience as an application scientist with both XRD and XRF. He has extensive experience in the use of both X-ray diffraction and X-ray fluorescence as it applies to the mud logging industry. Don Snyder is a geologist with diversified well logging and is their project lead for X-ray diffraction and X-ray fluorescence. She has 10 years experience in materials engineering, core analysis, surface well logging, and advanced geochemical testing. Today we'll review XRF and XRD basics, X-ray technology in oil and gas drilling, advanced mud logging techniques, how XRF and XRD are used on-site, and finish up with questions from the audience. This informational webinar is scheduled for about an hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of the presentation. The chat panel is not used for Q&A. If we're not able to get to your questions during the live webinar, they will be addressed personally by email or phone after the event. Now, without further discussion, I'd like to turn the presentation over to Jose Broom. Jose, take it away.
Thank you, Greg. I'm very glad to have the opportunity to be here today with Don Snyder to talk to all of you about the use of field XRD and XRF as it relates to mud logging applications. The development of field-based XRD and XRF instrumentation has really, in the past few years, expanded the use of these technologies in this industry as an on-site tool. In effect, it has had a huge effect in the time it takes to get the analysis, the cost of sending samples back to the main lab, and the ability to make decisions in real time. Don will be talking more specifically about how the mud logger uses these technologies. But first, I want to start with a basic introduction to XRD and XRF technology, and how they are similar and how they differ. So what is X-ray fluorescence? Very simply put, X-ray fluorescence uses an excitation source to excite elements, electrons within an atom. This excitation will eject an electron from its orbital, and there is a transition at that point from the next orbital, and this transition releases an amount of energy. This energy is directly proportional to the amount of that element within your sample. Quantitative element analysis, typically magnesium to uranium. It can measure from the ppm level to percent level for most elements. On this next slide, we're showing the user interface, how the operator first sees the data output from the instrument. It consists of a graphic output, as you can see, and to the right-hand side of the slide, it also gives you elemental breakdown, concentration, and statistical analysis. So that's the output for X-ray fluorescence. Typical detection limits are shown on this slide here. Typically, detection limits will vary with simple matrix, but these are some general rules that you can apply. So now we move to X-ray diffraction. X-ray diffraction is a direct mineralogy tool. It can offer qualitative mineral phase analysis, RAF range, concentration-wise, 2% to 100%. Other techniques can calculate or derive mineralogy, but XRD provides direct mineralogy, and this means that it identifies and quantifies the mineralogy directly from the crystal structure of your mineral. Continuing on to the next slide, the output of the analysis gives the user a series of peaks for the diffraction pattern. An example of the diffraction patterns is shown on the slide here. The diffraction pattern is then matched against a database of known compounds. There are publicly available databases like AMS-CSD that focus on mineralogical compounds, and there are subscription databases that can offer a wider range of organic and inorganic substances. The distinguishing difference between the two techniques are elemental versus mineralogy. Both techniques use an X-ray source as a detector. Both measure the response to X-rays interacting with a substance, and both provide measurement to help identify a substance. The difference is that XRF is elemental. So with an XRF, you would be able to analyze and detect iron, regardless of its state. With XRD, the same analysis will yield information such as hematite or magnetite, shown on the right-hand column. It also XRF will give you total elemental calcium, regardless of how it's structured. XRD can show you the polymorphs, calcium carbonate, calcite versus aragonite versus veterite. This is the main distinguishing difference between the two techniques. So with this brief introduction into the two techniques, I'd like to turn this over to Dawn Snyder at this point.
Thank you, Jose.
For her to go further into the how the mud logger.
Okay, fantastic. Many companies are now producing oil and natural gas from shale, a rock composed of mud and tiny fragments of other minerals, including organic materials. Oil from conventional formations is easier to produce because it's typically trapped in more permeable reservoir rocks, such as sandstone or limestone, that allow it to flow more freely. Conversely, unconventional reservoirs are characterized by tight formations that trap the hydrocarbons and require stimulation techniques to allow them to flow. Recent advancements in horizontal drilling and hydraulic fracturing have made the production of hydrocarbons from unconventional resources commercially viable. XRD and XRF are cost-effective, powerful methods for exploiting rich but I feel very underappreciated sources of data, the well cuttings. And a quick primer for anyone who's not familiar, well cuttings, also known as drill cuttings, they are the broken bits of rock and formation removed from a drilled borehole. These cuttings will vary from size and texture. They'll range from a fine sand to a gravel, depending on the type of rock being drilled and also the type of drill being used. To prevent the well from being clogged, the cuttings are carried back to the surface with a special fluid, which is pumped down the well to keep it clean and also to lubricate the drill bit and to control pressure within the well. This fluid is known as mud because of its appearance and consistency. As the drill bit grinds the rocks into the drill cuttings, these cuttings become entrained in the mud flow and are carried to the surface. On the drilling rigs, the cuttings are separated from the mud over a shaker screen. The mud is recycled to be used again, and the cuttings are usually disposed of. Part of a mudlogger's profession and science is capturing samples of these cuttings at very regular, close-spaced intervals. It's typically over the shaker screen that samples of well cuttings are collected. In using time-based calculations, the precise depth of the formation that the cuttings came from can be calculated. Okay, next slide, please. Finding the sweet spot. It is important to understand that not all unconventional wells are created equal, not just as between different plays, but also within individual plays. These reservoirs are heterogeneous, and outside of sweet spots, oil companies have to drill rock that yields much lower production performance. So operators are universally in search for that sweet spot, which implies the area of the formation where the hydrocarbons will best respond to fracture stimulations. In shale reservoirs, that sweet spot we're talking about are hydrocarbon types, relative brittleness, organic richness, thermal maturity, stratigraphic continuity, and of course your mineralogy. And using X-ray technology, we can now see changes within the rocks on the atomic and chemical level, and easily find and quantitate areas of wells that has more carbonates or more silicious and changes in the clay. The exploitation of shale and unconventional resources presents many challenges for the geoscientist. Deposits have significant variation from one basin to the other. So the key for success comes from targeting these sweet spots in the reservoir, evaluating the density and the structural orientation of their fracture systems. Shale clay sweet spots are typically characterized by mid to high kerogen content, lower clay volumes, higher effective porosity, lower water saturation, higher Young's modulus, and lower Poisson's ratio. Using these properties as a guide, reservoir engineers can define a productive drilling program. XRD and XRF analysis are well-known techniques of the petroleum industry that have been used for a long time in order to obtain reliable quantitative data to highlight various aspects important to reservoir assessment. High contents of clay minerals, for instance, may give a first estimation on porosities and permeabilities in siliciclastic rocks. Also, high amounts of dolomite and hydrite and salt may allow first assessments concerning porosities and permeabilities in your carbonates. Not only can XRD be plotted on these mud logs next to lithology descriptions, but data can be charted to discover formation tops, trends, and is especially important when identifying faults. Most shales are highly laminated. This presents a challenge for traditional analysis as they harbor consolidated and compacted parasequences of shallow marine sediment, clay, quartz, feldspars, and heavy minerals. They exhibit ultra to low interparticle permeability and low to moderate porosity and complex pore connectivity. Density plays an important role in analysis given the disparity between various components. For example, pyrite having high density in a smaller volume and kerogen having a larger volume percent than indicated by weight. So XRD mineralogy provides bulk rock mineral weight percent, and to be clear, this doesn't include kerogen or porosity. Brittleness, the likelihood of fracturing under stress is key. It is directly controlled by mineralogy and the fabric and texture of the mineral components. Accurate measurements of these minerals are imperative to evaluating the relative brittleness through a shale play, which can greatly improve your fracking strategies. XRD and XRF are also used in determining the contribution of clay minerals to the engineering behavior of rocks and soils. Ductile shale naturally heals, while brittle, silty shale with a quartz fraction is more likely to fracture. Geomechanical properties help determine the relative brittleness or ductility, providing valuable input into completion and fracture stimulation design. So your XRF, when integrated with your XRD together, can definitely help understand the rock strength and potential behavior. Your rock mechanics, such as Poisson's ratio and Young's modulus, as well as understanding the rock fabric, can be modeled with close correlation of the XRF compounds and elements. Here, I'm going to go over a few terms that describe the types of rocks and indicate oil and gas bearing zones. So, shale, it refers to a sedimentary rock that is predominantly comprised of mud, stones, and organic materials. Its low permeability means that hydrocarbons trapped in the shale cannot move easily within the rock except over geologic expanses of time, so millions of years. Shale oil refers to a shale reservoir containing the oil. The oil itself is the same oil found in conventional reservoirs. Likewise, shale gas is commonly used to identify natural gas produced from the shale reservoirs. There's no difference between this natural gas and the natural gas produced from conventional reservoirs. Now to flip it, oil shale is a term not used in reference to the reservoir, but to the actual type of sedimentary rock that is organic rich, fine-grained, and contains a solid organic compound known as kerogen. All oil and gas are ultimately derived from kerogen. Tight oil is a crude oil stored in shale and requires modern drilling and recovery techniques to get it out. And natural gas is also produced from shale deposits. Some of the key minerals and elements that are critical to understanding the unconventional reservoir are minerals that can indicate brittleness, such as quartz and carbonates, trace marker minerals and elements at boundaries, high trace metal values, especially vanadium, nickel, uranium, molybdenum, are all good indicators of organic richness. Minerals and elements associated with natural fractures. Pyrite and manganese can be indicators of oxidation and reduction states during deposition or early diagenesis. Clay minerals, especially expandable clays, and clays as they relate to clay diagenesis. Okay, next slide. Tightly steering the drill in the zones of the formation that will result in the best production in the sweet spots and the best part of the play is a very difficult skill, especially considering the bit may be tens of thousands of feet deep in X, Y, and Z directions. Geosteering is done with reference to geologic markers, such as the top and the bottom of your pay zone, and are typically defined using gamma ray or resistivity data. Having XRD and XRF data on site assists to define the zone boundaries to keep that drill in the pay zone. I've got an example of that on the next slide. Okay, or I guess it's one more down, but this slide shows just a few of the broad amounts of elements that can be monitored using XRF. And whether it's a particular element or a series of elements or elemental ratios, it's extremely easy to track and log the changes as you drill. Okay. Next slide. For example, okay, back to those trace metals such as the nickel or the vanadium or the uranium. These are all well known to have been deposited in conditions that represent persistent anoxic or eucentric environments, which are very important for the preservation of high amounts of organic matter. These trace metals are often concentrated in the shales. The correlation of elemental XRF with XRD helps also to verify the quantitative mineral interpretation and for your clay types. This next slide, this shows how using your potassium and your uranium and your thorium measurements, you can extrapolate, I like to call it a pseudo gamma, and it overlays and correlates very well with downhole tools. The direct measurement of XRD mineralogy and that elemental XRF from closely spaced cutting interval collection while drilling, it provides actually a higher quality and lower risk complement to wireline elemental capture tools. XRD and XRF can be logged at the same rate that matches most downhole collection reporting at typical drilling rates. When gamma becomes insignificant or tools fail, knowing the mineralogy can assist in calling tops, recognizing the formations, and staying in the pay zone. Back to that pseudo gamma, it is a great as an inexpensive backup tool for not if, when gamma sensors fail. Using XRF or the pseudo gamma log overlay has been very successful in difficult drilling operations, such as high pressure, high temperature wells where downhole tool failure is common and extremely expensive. X-ray diffraction provides easy identification of corrosion and scaling products with its on-site corrective actions. That's a great use to have this right on site. Certain clays and smectites will swell up in the presence of water. When they swell, they can trap the drill pipe and block up the well hole. Often in this case, you may want to switch to an oil-based drilling mud. All right, scaling. Seawater can combine with certain minerals, for example, your sulfates, to form scale both in the formation and in the drill pipe. If you see these minerals, you may know not to use a seawater-based drilling mud and to be very cautious using seawater in your nearby injection wells. All right, next slide. All right. The typical well in North America has between 25 to 50 fracturing stages or more, costing close to $250,000 per stage, with a typical production rate of only about 2% from these wells. That is a lot of money. What if we could reduce the amount of stages and increase the production from those placements? Placing stages in the most brittle areas of the formation will optimize production from those placements and provides an enormous reduction in cost, increases your production rate, and minimizes the environmental impact of fracturing. Understanding the mineral composition of these shale resource plays is particularly important with regards to the completion of your horizontal wells and maximizing that well performance. Steering these horizontal wells within the narrow pay zones at times with a comprehensive understanding of those rock properties is required to avoid geohazards and design effective hydraulic fracture jobs to stimulate the maximum volume of reservoir and optimize recoverable reserves. I'm really big on expressing that XRD and XRF at the well site do not replace traditional core analysis laboratories, but instead complements them as a screening tool. X-ray measurements on well cuttings are simple tests that look deeper into the rocks with more precision than observation alone. It doesn't replace the human on site because observations on color, texture, grain size are indispensable. XRD and XRF complements the mud logger, offering a precise quantification of the minerals, and that data is logged next to the visual descriptions and engineering data. Meticulous methods for the sample collection and the sample prep are essential. All data is reliant on that human at the shaker screens doing the frequent and accurate sample catching. And the resolution on the logs is also dependent upon how frequently those samples are caught. The more frequently, I mean as close as even 5-foot intervals, will provide the best resolution onto the log. Reservoir characterization is dependent upon the expert's working knowledge in applied geologic models. XRD and XRF help them provide indicators of geological history, your basin maturity, low-grade metamorphism, and in characterization of lithologies. Cavings. Cavings over the shaker are an operator nightmare. Stress fractures occurring in the formation adjacent to the borehole produces these cavings, which are carried along the surface along with the drill cuttings. They are common when drilling shale sequences and generally fall into one of two categories. There's blocky cavings that have a blocky appearance. They frequently exhibit microfractures on the surface. And then there's splintery cavings. These are very distinctive, being elongated and flat with a concave cross-section. An abundance of cavings of this type are strongly indicative of borehole instability caused by underbalanced drilling. The differential pressure allows swelling of the formation adjacent to the borehole, and therefore the appearance of splintery cavings is often associated with other indications of borehole instability, such as an increase of torque and overpull and drag while tripping. One of the greatest challenges is trying to determine where down the borehole these cavings came from. One great benefit of having XRD and XRF on site is that when problems arise while drilling, such as wellbore instability and fluid losses, if the pilot hole well cuttings were logged, you have an XRD, XRF fingerprinted well, and the subsequent cavings can be immediately identified to pinpoint the exact location of the losses. What we are looking at here is a typical log that incorporates mud logging and engineering, drilling, and MWD gamma data sets. But what's extra on here, you see the arrows pointing to, is a track with XRD information. You can see some arrows pointing to, you see the shale, which was the visual lithology, and I saw these cuttings for myself. That's exactly what they look like. Even under a microscope, they were very, very homogeneous. But once we were able to run the field XRD on them, Now we can see vivid differences in those visually homogeneous shales. With clarity, you can see areas of the well that have more carbonates, are more silicious, and places of changes in the clay. Now, on more of the spreadsheet level, the trace and the marker minerals have a myriad of applications in exploration and reservoir characterization. So not only can the well cuttings and shales appear to look the same, but gamma and resistivity tools often aren't sufficient to recognize tough steering situations, such as lateral facey variations, a dip change, and fault throws. Especially XRF data can help here. With that widespread of elemental data from magnesium to uranium that can be obtained downhole from the well cuttings in often 30 minutes or less, along with a large set of elemental ratios, you can quickly gain a very comprehensive understanding of your position downhole. Okay. From here, I'm going to turn this over to Jose to discuss output data for ID and quantification.
Thank you, Dawn. Great presentation. So once Dawn has collected her samples, introduced them into the instrument, run the analysis, our software program has the ability to provide a comparison plot of multiple samples, which is extremely useful when looking for trends, or more importantly, anomalies in those trends that you're looking for. The waterfall plot allows you to easily visualize the changes in mineralogy by the appearance or disappearance of peaks over the drilling depths, as the example shown here, circled in the waterfall plot. Picking out two of the diffraction patterns from that waterfall plot, we can look more closely at certain depths to see the changes in mineralogy. Here, we can see the change in composition from 2,600 feet to 6,200 feet. The changes are labeled accordingly. Once again, picking out two more patterns from the waterfall plot, we can see that even in as little as 400 feet, we can see the changes occurring. In this case, we can see where chlorite peaks disappear and elite starts to appear. Again, shown in the diffraction patterns. Speed of analysis and appropriateness of analysis length is always important. Our XRD systems use a CCD detector or camera, which captures the entire 2 theta range simultaneously. This allows the user to start seeing the pattern almost immediately, which is important when fast results are needed. As it continues to collect exposures, the signal to noise ratio improves, and you can decide when the results have shown what you need. Our customers typically are doing 5 to 10 minute tests, of course, depending on how much they care about quantification of the secondary peaks. Once the analysis is done, quantification using relative intensity ratio is then done. We do a quick semi-quant using XPowder, and we can set up a few patterns and turned into a push-button operation. We can select phases visually from a small database, and we can set up reference files for future quantification of similar matrices. What this allows you to do is go through the identification process automatically instead of one by one. Many questions about accuracy or comparison of field versus laboratory XRD. Most people wonder about how well the field XRD compares to the traditional lab-based instruments. This was a study from a drilling company where we compare the results from our Terra to a full-scale laboratory instrument. As you can see, the results showed very good correlation throughout. XRF output can be both graphical or numerical. So what you are seeing right here is a comparison, as Don talked about, of elemental concentrations versus depth. This is a small subset of the testing that we ran, but it shows very clearly an easy readout of XRF results. And typically this is what operators are mostly looking for, just a quick analog. So not only do the Olympus XRD and XRF instruments provide fast analysis, but having them on-site eliminates the time involved to send samples to an outside laboratory. This puts the information in the operator's hands almost immediately, allowing them to make decisions in real time. As you can see from the examples we've given during this presentation, there are many benefits for having these instruments in the well logging trailer as part of a routine analysis. They can provide more detailed information than was possible in the past. They can provide backup information and verification to other analysis tools, such as Don mentioned. They can provide data that can help optimize operations and better understand what's going on underground. In closing, I hope this presentation has given you some useful information about how Olympus XRD and XRF instruments can be used for mud logging applications. You can certainly contact us for more information or to schedule an on-site demo of the equipment. I would like to extend my sincere personal thanks to Don Snyder for joining us today, and also to thank Diversified Well Logging for allowing Dawn to collaborate with us on this webinar. At this point, if Dawn has anything else to add, I'll turn it over to her.
No, this is great. Thank you, Jose.
Thank you, Dawn. Well, at this point, we can answer some of your questions if you could submit them. And I see they're coming through. All right, so here's the first one. Are your instruments able to be used? Oh, I'm sorry. Are all of your instruments able to be used in the field? Yes, we have 3 different XRD units that offer different levels of field portability. The Terra is fully field portable XRD unit. It's built in a Pelican field case and can be run on batteries. So it's designed to be taken anywhere that you need it. The batteries can help with power fluctuations that can happen at remote locations, and the filter also helps to minimize dust. On the other hand, the BTX2 is a small benchtop XRD unit. It's small and lightweight enough to be moved around, but it is not designed to be as durable and rugged as the Terra. This unit can run on outlet power and doesn't require extra cooling. The Profiler is also a small benchtop with XRD and XRF capability. It also runs on regular power. It's small and light enough to be moved quickly and easily. For the XRF, the X5000 is just like the Terra. It's a true field portable instrument that can run on batteries and is also built into a durable field case. And by the way, it also has a computer built in. Another question, Jose, can the instruments handle external temperature variations? Yes, the instrument, all of our instruments have a cooling fan that takes care of any electronics needs, such as circuit boards, etc. The detectors themselves have a Peltier cooler, which is independent of that cooling fan. So ambient variations should not bother the instruments at all. Did you use RIR standard database? Or did you determine your own RIR? I'm sorry, we do use RIR, but I don't really understand the question. Maybe it could be resubmitted. Do you need to use multiple XRF calibration models to ensure optimal performance, especially in challenging light element analysis? No, not with our instrumentation. We've developed a very specific XRF software called GeoCam. GeoCam, in combination with a rhodium X-ray tube for the instrument, will handle large variations in both concentration and Z-weight of your sample. So essentially, the GeoCam calibration can take you from low ppm to 100% without changing calibrations. It's a very robust calibration, and no, you do not need multiple XRF calibration models. Yes, we have another one coming in. How do we get standards to build calibration in XRF? Well, as a company, we're not a standards provider, certified reference materials. There is NIST, ASTM, USGS, just to mention a few. If you go to those websites, they have many, many, many standards that will suit your exact needs with certificates of analysis, everything that you need. What parameters actually need to be known at the well site and cannot wait until lab and cannot wait for the lab analysis off-site? I may have misread the question. What parameters actually need to be known at the well site and cannot wait until the lab analysis off-site? Yes, I did hear you correct. I'll turn this over to Don. This is really more of a mod logging question for Don. Don?
Yeah. Okay. So field XRD and XRF, it's not only ideal to make fast drilling and geosteering decisions in the real time, it's also a cost-saving screening method to reduce the amount of samples you may have to actually send into a lab. A lot of times when you're sending enormous amounts of samples into the lab, it takes an enormous amount of time to get them back. And sometimes you really need some information just in some specific zones. So you can get through a lot of samples at a reduced cost. And traditional XRD labs are absolutely necessary for certain applications. They're absolutely necessary for studying true clay speciation and measuring clay expandability. Field XRD will quantitate the amounts of particular clay minerals, but if you have samples you're especially interested in, especially with their discrete clay properties, this is a great opportunity to screen through the bulk of your well, and then take those and send those to a traditional core analysis laboratory, and also get your results back from them a lot faster.
Thank you, Don. One more, at least. Can you speak a little about simple preparation for mud logging? What protocol do you need What do you need, electric grinder or manual? Again, sorry, excuse me for my hesitation. These are coming in live. So I'll take, this is really a two-part question. I'll take the first part in regards to simple requirements or instrument requirements. For the instrument, we supply a manual crusher with our instruments along with a 120 mesh sieve. Simply grind, sieve, load a small amount of powdered simple into the simple cell. In the case of the Terra and BTX2, they use about 15 milligrams of simple. That's about it. For the profiler, you would load 25 milligrams into the simple cell for XRF. The X5000 requires minimal simple prep. I'd also like to have Don address from the mod logger's point of view what the simple preparation requirements are. Don?
Yeah. You know, a question I get all the time is, how are you representing thousands of feet or, you know, an enormous amount of rock with such a tiny little sample that goes into the XRD? And the real key for this, although the machine does require just a tiny bit of powder in order to operate, the bigger your initial sample is going to best represent what's going on downhole. And then to split that evenly down so that you have the best chance of representing the minerals that are in the interval that you're interested in studying. The key, the secret sauce to accurate, repeatable, and useful XRD and XRF is always in the sample prep. And this begins with a human factor. Accurate sample catching and recording of that inventory is essential. Your next thing that's important is cleaning the samples. Depending on the type of drilling muds, whether you have water or oil-based or synthetic oils, the right solvent, the right surfactant, or right cleaning solutions need to be chosen. I can't definitively give an answer for the right solvent or the right cleaner for every single drilling mud because they're all unique. But if someone wants to email me more some questions, I can, after this, give them some recommendations for different choices for cleaning your samples and different types of drilling muds. So after they're clean, it's really important that you don't destroy some of the fragile minerals and clays that are inside your sample. It's best to air dry a sample with low temperatures. When you're crushing, it's best done by hand. Although a lot of these minerals seem really robust, you can actually break them down pretty quickly. And so the sample prep is the most critical part of a great diffractogram later. With the Terra, you absolutely have to get the particle size down to less than 150 microns in order to enter. But luckily, I haven't met a rock yet that won't get down to that size. So, and once you got a nice dry powder and great homogenization, and you really are set up to have a beautiful diffractogram through the Terra.
Thanks, Don.
Mm-hmm. That goes for the X5000 also. So same sample prep.
Just as a follow-up from me on this subject, Don, how long does the whole sample prep take from shaker to instrument?
If you have it down to kind of a systematic approach, without much effort or killing yourself, it's pretty easy to collect, clean, dry, grind, and run a sample and get results in 30 minutes. And even your MWD tools are typically about 60 feet behind the bit for when they're gathering information. And at most drilling rates, honestly, running a sample through XRD and XRF every 30 minutes keeps you in a similar zone as even the MWD tools do downhole.
Thank you. The next one is really a two-part question, so I'll answer the first part really quickly. can you use Rietveld analysis with your instruments? Yes, our data output is accepted by all Rietveld refinement packages available in the market today. And the second part of the question is, do you think that there is an advantage to use Rietveld method with the data quality provided by the instrument after 10-minute acquisition? Well, the use of Rietveld differs from company to company. Some use it and some don't. Rietveld is compatible with our instruments and software, and we sell a Rietveld program called Seroquant. But there are many others that can be used also. We've done studies that compare RIR results with Rietveld results, and it's shown very good correlation. So it's just a matter of preference and what engineers need. It depends on your, so closing, it depends on your needs, and it depends on the level of analysis that you're looking for. One more, are portable instruments less accurate than laboratory instruments? Quick answer, they're just as accurate. And on one of the slides going back showing data correlation between lab instrument and Terra field portable showed excellent correlation. So now, when used properly, our instruments will give data very comparable to much larger laboratory floor models. One more. Yeah, this one is really for Don. Do the types of additives used in drilling cause erroneous readings for XRF and XRD?
You know, I'm not sure who this is, but I'd love if they could direct me an email, because I'd like to send you over a paper recently addressing a similar question. Typically, they do not, because after we clean them off, what we're studying as a mud logger is what's inside of the rock, not what's coating it on the outside. And because of the drilling fluids and the muds we use, it absolutely has to be cleaned in order to study the formation. And so we're kind of breaking the egg open. After we get all the gunk off the outside, then we can discover the properties of the formations inside of those cuttings by breaking them down.
Thank you. Well, where has the time gone? Time's up. That's all we have time for right now. If we didn't get to your,
there's a lot of questions too on sample prep, and if anyone needs a little guidance or wants to contact me about that, especially for field instruments, I'd love to have more discussions with them on that at a later time.
Excellent. Well, right now it really is it. So thank you for submitting your questions. And I'd like to extend sincere thanks to Don Snyder, Diversified Well Logging. And now I'll turn it back over to Greg.
Thank you, Jose. On behalf of Olympus, I'd like to thank all the attendees for joining us today, and thanks to Jose and Don for their participation in this event. We hope this material presented was informative and useful. This webinar, along with the Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for participating, and we'll see you again next time.